Okay, part 2 of the conservation of energy tutorial. This has systems with a block and a block and a cat and a spring. And well, it's just one system, but we'll be looking at different parts of it. So the situation is that we stretch out the block on the spring, let it go, and it gains some kinetic energy, gains some speed. And we'll analyze this by first looking at system B, where we just look at the block itself. That's the object of interest. There's no other components to that system. And then we'll look at system SB, the spring and block system, where we look at the block and the spring as kind of this single connected object. Okay, so first question, list all the forces acting on each system after you let the spring go, so that the hand force is not involved anymore. The hand lets go and now the system moves. So if we just look at the block, the forces acting on that block, obviously there's the spring force. So we have the force from the spring on the block. That's pulling the block to the left. And now we have two other forces that are kind of irrelevant, but I'll write them down anyway for the sake of completeness. There's the gravity force of the Earth pulling down on the block. And because we're about to use the symbol W for work a whole bunch of times, I'm going to write this as Fg, gravity force, of Earth E on block. And there's the normal force from the ground. Normal force of ground on block. So that's what's going on for system B, consisting of just the block. Now, system SB, that contains the spring, we don't include the force of the spring acting on the block, or the Newton's third law pair of the block pulling on the spring, because those are the system. These objects are that system. We need to look at what forces are acting, what external forces are acting on that system. The external force that's acting on the system is the force from the wall on the spring. The wall is pulling on the spring. So I'm going to write that as the force of the wall on the spring. And then we have these same two forces as well. The gravity force of the Earth on the block. We're ignoring the mass of the spring. It's a massless spring. It's a very small mass. And we still have the normal force of the ground on the block. Okay, so the idea here is when you consider a system, whichever one it is, you only look at the external forces acting on that object of interest. Our first object of interest was the block by itself. Our second object of interest was the block and spring system as a whole. So in part B, we'll determine whether each of these forces does positive, negative, or zero work on the system, on the object of interest. Okay, so we'll start with the block only system and look at the spring force on it. Now, from the block's point of view, the spring is pulling it to the left and the block is moving to the left. So there's a force and a displacement. The force and the displacement are in the same direction. So that means the work done by the spring on the block is positive. Now there's this gravity force that's pulling down, but the block is moving to the left. The force vector and the displacement vector, the force vector and the displacement vector are perpendicular, so there's zero work done by gravity. So the work of the Earth on the block is zero. And similarly for the normal force, which points up, that's also perpendicular to the displacement. Zero work from the normal force. Whoops. The work done by the ground on the block is zero. B for block. Okay, so only one of these was positive, the work done by the spring on the block. Now, let's look at the system of both of these objects connected together. The first force we identified was the force of the wall pulling on the spring. But the wall is not moving. So, in order to have a work, the displacement has to be non-zero. That wall is providing a force, but the wall is staying in place. So walls do no work. Walls are almost always stationary. Walls never do any work. So the work done by the wall on the spring is zero. And then we have these same other two forces as before. For the same reasons, they both do zero work. So there is zero external work done to the spring block system. There is positive external work done to the block only system. So the net external work, like we just said, is positive for block only and zero for the spring block system together. So two students are considering the work done on the two systems. Student 1 says, I think that the spring does positive work on the block. That's right. And the wall does positive work on the spring block system. That's not right. The wall doesn't do any work because the wall doesn't have a displacement. The wall doesn't move. So student 1 was only half right with that statement. Student 2 says, but the point where the wall exerts a force doesn't move, the displacement is zero. Student 2 is correct about that. For each system, determine whether the change in potential energy over the interval is positive, negative, or zero. So here's question E. For system B, consisting only of the block, there is no change in potential energy. There's no change in gravitational potential energy because the block isn't moving up or down. And there's no change in spring potential energy for that system because that system doesn't include the spring. Okay, for the system consisting of the spring and the block, now there is a change in potential energy. The system starts out with the spring stretched, so it has a large potential energy, and then at the end, the spring is no longer stretched. It's at its relaxed equilibrium length. So the potential energy at the end is zero. So we started out initially with a large potential energy and ended up in the final situation with zero potential energy, which means that this change in potential energy for the spring block system is negative. It lost potential energy. Part F, two students are considering an energy analysis of system B, the block alone. Student 1 says the spring does work on system B. So system B's spring potential energy changes. Student 1 is incorrect because, once again, system B does not include the spring. The spring is external to system B. So we don't include the spring potential energy. Student 2 says, I agree that the spring does work on system B, but there aren't any springs in system B, so how could it have spring potential energy? It's just a block. Student 2 is right. Question G. For which system is the total energy unchanged over the interval from T initial to T final? So remember, we have this relationship between external work and change in total energy. So if you have 0 external work, then you have 0 change in total energy, right? We had this relationship, the net external work equals change in total energy. So for the system consisting of the spring and the block, we had 0 net external work, so there's 0 change in total energy for system SB. Did I answer the question right? Yeah, for which system is the total energy unchanged? System SB has total energy unchanged. For the system for which total energy changes, explain how you can account for the change in kinetic energy of the block in that system. So what's going on here is because, so that also equals delta K plus delta U. So if there's 0 net external work, then we have this relationship, and that must mean that the change in kinetic energy is minus the change in potential energy. So what's happening in the spring block system is that it's initially stretched out. It has potential energy, spring potential energy initially. Now you let the system go, and there's a negative change in spring potential energy and a positive change in kinetic energy. And so those two changes, this positive change in kinetic energy and negative change in potential energy, are exactly the same amount, and they add up to 0. So energy is conserved in system SB. In system B, we didn't include the spring, so the spring was the thing that was doing external work to the system, and the system's total energy increased in system B because that external force of the spring did work on it.